Hello everyone and welcome to this HFWorks webinar. So today we're going to speak about the design and simulation of a miniature multi-band antenna for the Internet of Small Things or the Internet of Things. As many of you know, that Internet of Things is a hot topic nowadays, so that's why we chose this important subject to talk about it and see how we can model antennas, small antennas using a HFWorks product. This is our overview, so this is our agenda, small introduction, design challenges and design details, and we're going to show some results and live demonstration and the conclusion. Alright, so the Internet of Things is a term used to describe any application that are connected through the internet. So, or things are interacted through the internet. The Internet of Things help people live easier, work smarter, and gain complete control over their lives. So this is a figure of the Internet of Things, and as you can see, almost all our daily life is affected and has some applications. So whether in your car, agriculture, home appliances, where your fridge will talk to the microwave is going to talk to your smartwatch. Your smartwatch is going to talk to your maybe pacemaker for biomedical and healthcare. So all of this, okay, energy, smart cities, smart homes, healthcare, transportation, smart manufacturing. Okay, there are some studies actually, according to Cisco. Okay, by 2030 there will be 500 billion devices connected to the internet. So it's really exploding, the Internet of Things. Okay, and of course, all of this thanks to electromagnetics. And when you say electromagnetics, these devices, they must have an antenna. Each one of these must have an antenna, and the most popular antenna used for internet of things is just a regular whip antenna, PCB or chip antenna. All right. By their nature, the wearable or embedded devices are small. Okay, and smaller is better. Okay, why? It's neater, it's cooler, consumes less energy, less weight, easy to install at the IoT terminal. So there is a trend in the miniaturization of IoT devices. But the antenna, despite it is small, it must perform, okay, like any other antennas, like a regular large antenna. So that's one of the issues. So that's why we topic today, the Internet of Small Things, because things are getting smaller and smaller. Okay, and that is going to really affect a lot the antenna industry for the Internet of Small Things or the Internet of Things, because for the Internet of Things, of course, you need a good radiation efficiency, multi-band operation, and most importantly, miniaturization. The miniaturization is very important for the Internet of Things, because again, devices are small, so they're going to need a small antenna. And we know electromagnetics for long time that the small antennas are actually a nightmare for antenna designers for many decades. Well, one way to get around it is to go higher in frequency, such as terahertz. Okay, because as you go higher in frequency, wavelength smaller. So what is physically small, it becomes electrically large. And when it becomes electrically large, it radiates better. But unfortunately, terahertz, in nature, there is no free lunch. Okay, terahertz frequencies, there are new applications coming, but they have some big limitation. One of them is the rapid decay and strong absorption by water. So these are big limitations. They could definitely turn that. Terahertz will be really good potential to get around this small antenna paradox. Okay, among small antennas, okay, the PCB antennas for the Internet of Things are becoming more and more popular. Why? Because they are effective due to their balance, because they are effective, and they provide a balance between gain and size. Chip antennas, unlike chip antennas, PCB antennas can operate over a relatively large bandwidth with relatively high gain. Okay. All right. So is it possible to miniaturize PCB antenna without sacrificing performance? That is the $1 million question, and that's what we would like to answer today. So one way, the PCB antennas, they have a big advantage because you can use structures, okay, Meindner structures, okay, that allow the reduction of size of the antenna while keeping the same operation characteristic, okay, like meander lines or zigzag lines. You can also use slot, can be added to obtain multiple resonance necessary for multi-band operation. Extending the meandered structure on the back layer of the substrate to exploit the limited available space. So this is one advantage of the PCB antenna. You have the upper, the main face, okay, but you can also use the back plane to extend the capability of your antennas, okay, as we're going to see later. Small change in antenna dimension this is one problem, okay? Small changes, because the antenna is small, okay? A small change can have a large impact on the performance of the antenna. In particular, for a PCB antenna, we need to find the optimal dimensions of the PCB in order to achieve a good performance. Of course, good performance means good gain, good efficiency, small VSWR, and so on and so forth. Okay. Another issue that we would like to answer today, okay, you have an antenna, PCB antenna, but that PCB antenna must go in a casing. Okay. Now, does the casing affect the performance of the antenna? We say yes. Okay, but we will see later on, okay, the effect of the casing. So the casing has also must also be carefully designed. Now, what are the performance metrics of the antenna? Okay, of course, VSWR is one metric, so we have to see how good of a matching is reflected in the value of VSWR. Of course, the closer to 1, the better is your antenna. The efficiency, high efficiency antenna, they eat most of its power, so that's important. And the gain. The gain, of course, the higher the gain of the antenna, the better is the coverage. So these are basically 3 metrics that we would like to use today, and use most of antenna engineers. They use these metrics, antenna metrics. Okay, we're going to use these metrics today to study this miniature antenna. All right, let's look at this antenna that we're going to study today. Okay, so it's a printed inverted F antenna. So this is the main, this is the what we call the main arm, okay, and this is a feeding. The port is right here. We had dielectric. In addition to that, based on the meandered inverted F structure, we have this secondary arm of the antenna, and that plays a very important role, as you're going to see in the results later on. Okay, because you have limited space, there is 4 V's, okay, that they communicate between the main plane and the back plane, or okay. All right, let's look at the structure now. Okay, so this is the antenna that we would like to study today, okay, for an IoT or mobile terminal. Okay, a casing is a box of lossless, this is the casing, plastic material that surrounds the PCB antenna, and this is the battery. The battery is fully made of copper. So you have the battery, dielectric, the casing, the feeding is right here, and this is the antenna main loop, okay, and the secondary loop is in the back plane. All right, let's see. Okay, so now these are some of the results obtained by HFWorks, and let's look at this now. L1, this is the main arm of the antenna, okay. We want to see the effect of the L1 and the length of L4 in the back plane. What is the effect of these parameters on the performance of the antenna? Okay, let's look at L1. This, okay. So we can see that actually this one is the L4, okay. At L1 equal 11.5 millimeter, we looked at L4 19.5, 20.5, 21.5. As you can see, okay, both the first and second resonance, okay, and especially second resonance, and kind of shifted. So from this parametric study, we can see that the optimal value for L4 is 21.5 millimeter. So this is one first conclusion, okay. The L4, okay, or the back plane, length of the secondary arm, okay, the back plane does affect both the first resonance and second resonance. And the larger is actually 21.5, it gives us the best resonance for the resonance frequency. Okay. Now, of course, we cannot keep increasing L4 indefinitely because you are limited by the physical dimension of the back plane. Okay, let's look at L1. L1, unlike L4, doesn't have any effect on the first resonance. They're all the same, okay? But it does have an effect on the second resonance, okay? So looking at L4 is fixed at 21.5. We varied L1 from 9.5 to 11.5, okay? And as you can see, there is a clear shifting to the left of the resonant frequency of the second resonance. So again, the longer is the L1, okay, and as expected because it is electrically larger, okay, you have a better or smaller resonant frequency for the second mode. Okay, so this is the first conclusion from this parametric study. And again, these results obtained using HFWorks. Okay, so the slot dimension is modified by varying L1. When it increases, just mentioned, okay, there's a shift. So the optimum value for L1 is 11.5. So this is our first conclusion. Now, let's look at the VSWR. Second question you want to ask is the effect of the casing. Okay, what is the effect on the VSWR? So the blue is integrated with the casing, okay, and the red is isolated. Okay, we can see, okay, there is really, because this antenna and the boxing and the casing is optimized, there is really not much difference. Okay, so this is assuring, because despite the fact that we cover the antenna, we still have good VSWR at 3 different resonances. Okay, and of course we want to achieve smaller VSWR. Okay. Okay, so it causes a small shift. Okay, when you put the battery and the casing, okay, to a lower frequency, but really not significant. Okay, so it's an acceptable shift. Let's look at the antenna efficiency. And antenna efficiency is, you take the radiated power divided by the input power. High efficiency, as said earlier, means the most of the power at the antenna's input is radiates away. And of course, if you have low efficiency, means the power loss, because it is mostly absorbed and reflected due to the impedance mismatching. Okay, now so let's look again at these results. When we integrated the antenna, integrated meaning we added the casing and the battery, okay, compared to the isolated, okay, there is a small loss of efficiency at this frequency here. Okay, but again, of course, depend on the design. It's on the specs. Okay, and if you're an antenna designer and making this type of antenna and selling it to telecom companies, okay, they may argue about this. Okay, there's some loss of efficiency, but we don't see it's a lot. But in any way, this is not the most optimal optimization or device antenna structure. But for this, we see this small difference right here. But for second and third, really, there are barely no differences in the efficiency of the antenna. Okay. What else? So, yeah, in percentage, mostly it's quoted in percentage, by the way, the antenna efficiency. Okay. Okay, so we see some efficiency at different frequency bands. Okay, this is around 40%, around 27.5 and 16.5 at the GPSL2 band. Okay. Okay. Because this antenna was optimized, we achieved a dipole-like radiation pattern. Beautiful pattern. Okay. That is actually is not. I'm sorry. Is not. Let me go back. Previous slide. No, I'm sorry. Gonna go back here. Okay. So the far field or the antenna gain pattern, okay, is not affected at all, almost no difference really between the integrated antenna isolated, and then it's expected, you know, because in the far field is less sensitive to the small variation. So, and because this was optimized, we're able to obtain this beautiful dipole radiation pattern. Okay, so HFWorks is integrated in SolidWorks. So this is SolidWorks and this is HFWorks. So there is no need to export your CAD or heal geometry, clean geometry. Really, you don't need any of that. And this is one of the powerful features of HFWorks. Is a gold certified by SolidWorks and is fully integrated in SolidWorks, as you can see. So this is SolidWorks, this is HFWorks. So just a tab. So we're not going to explain how you create geometry, just refer to SolidWorks, and it's very easy actually. It is one of the most popular 3D CAD packages. Okay, but rather we're going to jump straight to the HFWorks studies. Okay, so first study is a parametric study, and you put parameterization, saving 3 field and 3D field data. Frequency is between 0.8 and 1.8 gigahertz and 101 frequency point. Okay, material, you know, applying material. This is just push button commands are straightforward. We have many YouTube, in our YouTube channels, we have many videos explaining how to apply material, ports. In this case, this is your port, is right because it's an internal port. Okay. So this is structure. This is your battery. This is the main antenna. Okay, PCB antenna, or we call primary arm, and the secondary arm on the back plane. Okay, the casing, if you want to put the casing, this is the casing. Okay, and the first study is without casing. We just simply put the material of the casing air. That it means equivalent to saying there is no casing. Okay, let's look at what we have design scenarios. In the design scenarios, we're varying L1 and L4, and we have these different scenarios. Okay, let's look at the results. Okay, first sets of results, we can see the results table. While the results table for each scenarios, okay, we have an each frequency. We have the what we call circuit parameter, the S matrix, the normalized S matrix, impedance matrix, admittance matrix, ports results, okay, and the VSWR, okay, at each frequency. Of course, you can export this to different format, text file or CIT, SPC file or touchstone or any other format that you require if it's not there, if you don't have it. Okay, you can print, of course. Okay, and to close the results table, just click close. So these are basically table results. You can also plot. Okay, and now I plotted the this one this for different L4. Okay, as showed earlier, the L4 is fixed, but L1 varies. In the PowerPoint, we showed this plot, but just to show you that yes, at first resonance is not dependent, much dependent, or actually is not dependent at all on the length L1. Okay, but the second resonance does depend on the L1. So you see there is a shifting in the resonance, and the longer the L1, 9.5, 10.5, 11.5. The green is 11.5. Okay, so this is one first set of results you can obtain using HFWorks. You can see it in a listed format, a text format, of course. You can say print as just a regular 2D plot, so you can do a lot of things with that. Okay. Second set is the effect of, now L1 is fixed, but L4 changes. Okay, there is some variation, as we said earlier in the PowerPoint presentation, okay, in the first resonance, but there is a significant difference in the second resonance. Okay, and just to remind you that the L4 is the length of the secondary arm and the back plane. Okay. We can also plot the electric field. Okay, this is near field data. Okay, and we can, because we have different scenarios, we can animate versus scenarios. You can see. We can also do a vector plot, and we can animate this time versus phase. We can also do a section plot, section clipping, for instance. Okay, and they can plot on section only, and then they can change the plane. There you go. Where is it? Okay. Can also animate. Now I have three choices: versus phase, versus scenario, and versus section cut. Okay. So now I can change my. You see, I'm changing my section. There's another neat feature, is the 2D plot. If I wanted to see the value of the field, say you want to see between this point, these different points over here, okay, and now at the first scenario, okay, and now you can see this is how between the segments, this is the distance between segments, I can clearly see how my electric field varies, and I can see it in text data if I want to. Okay, all the plots that we've seen, we can do them. You can apply them. So this fringe, vector, streamline, 3D point, 3D mesh, 2D, all of them for electric, magnetic field, ports field, loss density. This is like, say, this is volume loss density, okay, surface loss density, and of course this is a surface loss density. It happens here in this case only in the vias. Ports field, okay, this is my electric field, okay, at the port. So any of them, any of these plots, you can all of them, they have the same feature, okay, that I showed for the electric field. We can also look at the polar plot, okay, for this particular scenario, okay, or 3D, okay, pattern, okay, and I can create a report. Okay, maybe I'll show it in the next study. Okay, so this is the first study, is a parametric study that parameterized L1 and L4, and we saw how the S parameter, the field also. Again, let me go back to this field. Okay, if I edit definition, okay, I can choose different scenarios. Okay, and at each scenario the values change. Okay, and of course at different frequencies too. Okay. Now the next study that I want to show you is this one. I want to compare an antenna isolated. So when it is isolated, okay, the casing is air, and the battery, I don't need to do a new model, okay? It's the same geometrical model, okay? But by making the battery air and making the casing to air, it means it's just the antenna. It's isolated without the battery and the casing, okay? And then in the second case, I have this time the casing is plastic and the battery is PEC or copper in this case, okay? And now I'm going to look at the results, okay? Let's see now, this is my VSWR. Okay, so my VSWR versus frequency for the integrated antenna, the blue, okay, or the isolated antenna, the red, okay, I can see there is some effect of the battery and the casing, but is really not significant. Okay, so so I can zoom in. Okay, where's my okay? Yeah, so there is some, okay, but not significant. And again, as I said earlier, it could be, depends on the specs and of the antenna and desired performance, you know, but definitely HFWorks allows you to see the effect of the battery as well as the casing. So this is first set of results. Second one, I'm looking at S11, okay, and again looking the effect of this is integrated and this is the isolated, okay. There is some effect, though not a lot, due to the integration of the antenna, okay. So it's really not much difference. So as far as S11 is concerned, I can safely say that really the integration, I mean adding the battery as well as the casing does not have a lot of effect here. But the idea here is not really to show you how good the design is, okay, because we are not antenna designers really. We are simulation people who just trying to explain to you that HFWorks allows you to study this effect, the effect of adding battery, adding a casing, changing material, changing frequency, okay. That's S11. Total efficiency of the, again, this is the efficiency of integrated versus isolated antennas, okay. And again, for the first resonance frequency, there is some slight differences, okay. So this is the total efficiency of the antenna, and this one again, as we said earlier, the far field, the 3D antenna pattern, okay. Last thing, once you're done, you can actually generate a report. Let's go document, okay. My name is Ahmed Kabir, the company name, HFWorks, and you can create an HTML or a Microsoft Word. That's going to dump all the information on this report. So you don't need to take notes anymore. So this is your nicely formatted. all the information about the geometry, the mesh, the material, the excitation, study properties, okay, and then results table. Everything is in the report. It's a long report that has all the information, of course, because it is an HTML file. You can share it on the internet. You can produce a PDF file, okay, so on and so forth. So now it's time to conclude. Okay, the conclusion is the Internet of Things becoming the Internet of Small Things, because devices are becoming smaller and smaller and smaller. The Internet of Things or devices, as I said, Cisco projects of 500 billion devices worldwide uh, connected to the internet by 2030. So it's really, there's a huge potential for the Internet of Things or Internet of Small Things. Okay, number one. Number two, because the uh, the antennas, because the devices are smaller and smaller, they require, of course, every device terminal, it needs an antenna. That's how it communicates. Because devices are very small, okay, it needs smaller and smaller antennas. And smaller antennas are difficult to design because radiation, and they don't radiate as good as a large antennas. That's why in the airport you see big antennas, because small antennas don't do the job. But there is one important uh, uh, point here. The Internet of Things, the range is small, okay? So you are in a room, maybe within 10 meter, 20 meter, that is, or 30 feet or 60 feet, okay? Most of the devices are in the near field, okay? So despite the fact that it's difficult to design these antennas, okay, it is uh, it's okay, they work fine because the range is not is short range, okay. Nevertheless, it's challenging to design small antenna for the Internet of Small Things. Now there are whip and chip antenna and the PCB antennas. The PCB antennas, they have are more popular because you can really achieve better performance with the PCB antennas. In the PCB antennas, you have a lot of room on top and bottom of the substrate. You can create slot, meander lines, and so on and so forth, but you need to optimize. Without optimizing the dimensions of the antenna, you cannot achieve a good performance of the antenna. HFWorks is really your ultimate tool, okay, and your companion. It can help you optimize your antennas and compare the S parameter field, optimize by parameterizing, by creating different studies. So if I wanted to, for instance, if I want to create a different study now, just I create this one, it's just a copy, say copy 2, okay? And you can create as many as you want. Okay, now I can modify the study. I don't need to redo the whole work with material or the port or the mesh. Just can rerun the study by modifying whatever input I want. And better yet, you can, before going home in the evening, you can run all studies. So it's a powerful tool. It's a power antenna tool that can help you optimize your small antenna. And with that, I would like to thank you. And the floor now is open for question. Please type your question on the chat region on the right hand side. Okay, thank you.
Hello, everyone. My name is Nisreen. I'm a senior application engineer. Thank you for joining our webinar today about miniature multiband antennas for the Internet of Small Things. So I'm here to answer your questions. The first question, can you embed within the antenna discrete components such as chip capacitors or inductors, ideal or with known S parameters? Yes, sure. We can simply add lumped ports. We have the lumped ports, the lumped elements boundary conditions in HFWorks. It's used to define access surfaces to the structure. They must be planar surfaces. So you can use the lumped elements as an RLC boundary condition, and then set the values of lumped resistors, inductors, or capacitors. So you need to set multiple RLC values in parallel or series combinations. The second question, can you superimpose the antenna artwork on any shape of surface? Yes, yes, you can, but it may affect the results. So, because the size and the shape will affect the total efficiency and other antenna performance. So you need to study this carefully and do simulation. Because you need to create the correct ground plane and place the antenna in the best and choose the best placement of the antenna. For example, if you want to put the antenna on to place it on the PCB, it's generally recommended that you place it on the corner of the PCB. It's the optimal position to get better performance. Another question, can you break the radiation field into different polarizations? Yes, sure. Using HFWorks, you can create different 2D polar plots by setting the phi and the theta values. You can also create the co-polarization radiation patterns. Any other question? No more questions. So I hope you enjoyed watching this webinar and find it useful. Our webinar will take end now. If you have any other question, feel free to contact us by email. Please don't miss our future webinar. We offer you free weekly webinars, so you can go and check the list of our webinars in our website and choose the one you find interesting to attend it. Thank you.